Welcome to tutorial 21 entitled Displaying Numbers, and in this tutorial we're going to investigate how we can display a 4-bit binary number as a decimal number. We're going to be using an IC which is numbered the 4511, which is a BCD to 7-segment display decoder, and we're going to need a 7-segment display with that as well. Let's just have a very quick look at results from the previous tutorial, because we need to just understand what we mean by a 4-bit number. So in the previous tutorial we built, using D-type flip-flops, a 4-bit counter where the values were 1, 2, 4 and 8. A, B, C, D. So least significant bit to the most significant bit. Now the problem with this is, when we had it on LEDs displaying, say for example 1111, we have to work out what they're worth. Well, if they're 1, 2, 4 and 8 added up equals 15. So for example, if we take the number 9, it would have shown on the LEDs on, off, off, on. So let's have a look at what we're going to do here. A couple of things we need to look at. First of all, here is our 7-segment display. A 7-segment display has, as is fairly obvious, 1, 2, 3, 4, 5, 6, 7 segments. They are labelled A, B, C, D, E, F and G. We'll come on to this one later, the DP. And the numbering on them, when we look at them, is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Opposite 5 is 6, 7, 8, 9, 10. Now, when we connect one up in the circuit, if we want to connect up to segment A, which is this segment here, we can connect to pin 7. So that would be 5, 6, 7. So we would connect to that pin. We're going to be using the 4511, this driver decoder chip. And therefore what we would do, we would connect segment A, which is pin 13 on the 4511, to pin 7 on the 7-segment display. So if we would connect, let's say F, which is this segment here, this will be connected from pin 15 on our 4511 to pin 9, 6, 7, 8, 9 on our 7-segment display. This chip is fairly unusual in that we are going to be using every single pin. So once again, we have pin 8, pin 16, notice it's a 16-pin chip. They're the power pins. We have all of our outputs going to the 7-segment display on the top half, and on the bottom half, let's break it down. We have D1, D2, D4 and D8. These are our 4-bit data bits, i.e. our 4-bit binary number, weighted order, least significant bit to most significant bit, A, B, C, D. We also have these pins here, LT with the bar above it, BL with the bar above it, and the store pin. And I'll explain what all those mean later. So when we wire it up, right at the beginning, ensure that LT and BL are made high, and ST, the store pin, is low. And then we're going to connect A, B, C and D, so D1, D2, and I've called them D3 and 4 here just sequentially, but i.e. D1, D2, D4, D8, so they are low. And the display should show a 0. So, all that is done. And here is my board all built for me. So we can check that everything works. At the moment, all these inputs are low, but when we flick a switch, they will go high. When we flick a switch, it will go high, etc. because we have pull down resistors. One more point. I know this is probably not easy to see, but on the 7-segment display, on the bottom it says SC. That's very important. That means it is a common cathode display, not SA, which is a common anode display. Because if we look at the way that these are drawn, pin 3 and pin 8, I'm using pin 3 in my circuit. So I look here, pin 3 is going down via this resistor to ground. Therefore, highs from each of these going to each of these means that the LED will turn on, because if this is high and this goes down to ground, current can flow from positive to negative. Common cathode. So, all we need to do, first of all, we are going to enter our binary words A, B, C and D. So I've labelled them 1, 2, 4 and 8, hopefully making the maths a little easier. And at the moment they're all 0, and on my display I have 0. Correct. Next I'm going to put A1. So I slide A up and my display goes to a 1. Next, A goes down and B goes up. 2. Next, A and B are both high. I'm going to do all this quickly. So then C goes high, then C and A, then C and B, then C, B and A. Then put them all low again, D. So when D goes high, then D and A, and at that point I'm going to stop. So far we've done So we've got to 1001, so D is high and A is high. Next, we have D and B high. So I'm going to put A low again, so that should go back to 8. And now I'm going to put B high, and watch what happens. So the display has gone off. Next is A high. Next is D and C high. Notice I put B and A low and it's gone back to just D. So D and C, D, C and A, D, C and B, and then D, C, B and A. And it remained blank all the way through. Blank all the way through down to 1111. So we know from previous example that 1010, which is 1, 2, 4 and 8, so 2 and 8 should have been 10, which of course makes sense because we've counted from 0 to 9 here. So that would have been 11, 12, 13, 14 and 15, which is the maximum number that we can display. So what's happening here? First of all, what happens for values above 1001 and why? Well, quite clearly, we have a single 7-segment display. The biggest number that we can display on here is a single digit. Therefore, we can display from 0 to 9. Anything above 9 can't be decoded onto a single digit, and therefore it goes blank. So the maximum is the number 9. I could draw it like this if I wanted to. Above that, it goes blank. What happens if you make ST a high and change the values of DCBA? Well, what I'm going to do, I'm going to put them all back low again so that we have something on our display. And here is my ST, which is currently low. And I'm going to make ST a high, which I've done. And 0 is still being displayed, but now I'm going to change it from 0 to 1. And nothing has happened. Let's try changing it to 3, so I'll change B as well. Nothing happens. So let's put ST back low again, because clearly with it high it's stopping, and immediately the 3 that we put on there is displayed. So I'm going to put ST high again. Let's slide up C, so that should be 1, 2 and 4, which is 7. No change. Let me slide ST back down, and now 7 is displayed. So ST, which is the store, is stopping the display showing when it is a high. So what happens if you make ST a high and change the values? The number does not display until ST is low again. What happens if you make BL a low? Well, let's go to BL. My BL is this pin here, and I'm going to slide it low, and my display has gone off. If I change anything, if I put a 0 in here, no change. I'm going to put BL high again, and there we go. I'm on 0 here, and I'm on 0 there. Now BL actually is known as blanking input. Blanking, which means it blanks the display. It's a way of turning off the display if you make BL a low. What happens if you make LT a low? Make sure that BL is high though. So we've made BL high because we've got a display. So I'm going to make LT low. I'll tell you what I'm going to do to make this more effective. I'm going to put A high. So therefore it displays the number 1. And now I'm going to make LT a low. And immediately the number 8 is displayed. Now it's not about the number 8. What that is every single one of the 7 segments is now on. It wouldn't have mattered had I been on the number 3 and then put the BL low. 8 or all of the 7 segments would have been displayed. And what this pin is, it is a light test pin. That's what LT stands for. In other words, all segments, in other words all 7, are turned on. It's a good way of checking if anything is broken within the 7 segment display. What does the bar above BL and LT indicate? If we have a quick look at our 4511 pinout, you'll see that LT and BL both have bars above them. And when you've seen that bar before, it generally means something is not something. But what it actually means is in this case, it's an active low. So in other words, we normally hold both LT and BL high. Here they are high. And when we make either one of them low, they do their job. In other words, they are active, they are turned on. So the bar indicates it is active. In this case, active blanking or active LT, lamp test, or light test as it's also known. Finally, wire up pin 5 of the 4511, which is our DP pin, this pin here which we haven't used today, and see what happens. Now it's best to do this through a current limiting resistor. So if I just slip this back to show the number 1, and here we go, I'm going to connect it now. Can you see what happens? You will see this little decimal point come on, and that's what the DP stands for. So should you ever want to use the decimal point, then you just connect it to 5 volts and it will turn on. But it's not part of the decoding process. Finally, just to explain very quickly what we mean by, sorry, there we go. This is a BCD, binary coded decimal. In other words, it's decimal, a decimal number that is being decoded from a binary number to this 7-segment display. It is a latch, which means the number is latched on, it stays on. Decoding and driver. In other words, it's able to supply enough current for 7 LED displays. So in activity 2, what we're going to do, we're going to connect up our 4-bit counter from our previous tutorial, in which we used our D types, where the output cues formed A, B, C, D, which are D1, D2, D4, D8, least significant bit to most significant bit, but we built it the other way around with the LEDs representing the binary number. And let's have a quick look at those results. So as you can see here, if you remember, 1, 2, 4, 8, A, B, C, D, and we had 16 different possible combinations from 0 to 15 as the outputs. And we are going to feed those into our circuit that we've just built here. So this is the 4511 into the 7-segment display. And these were our switches, our data bits. And we're going to remove these and connect in those D types. So let's just remind ourselves how that counted first of all. So they were all off, and as we press the switch, we have the clock as a rising edge going in, and we go 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then back to 0. So we're now going to connect those 4 outputs from the D type into our 4511 into the D1, D2, D4, D8. Now I'm connecting them in and I'm leaving the LEDs in the circuit at the moment. I'm hoping that this will work. Sometimes it doesn't because the LEDs interfere with the signal, because of course we have a voltage drop across the LEDs. So because this is a digital circuit and the voltage will have dropped here because of the LEDs, it might mean that the logic signal is not right, but we'll look at that if that happens. So here we go. Good, seems to be working. 1, 2, 3, 4, 5, 6, 7, 8, 9, and remember what happens after 9? That will go blank because it can't display 2 digits. So if you like, it's confused. But of course our binary is continuing to count. So that is now 10, 11, oh, that jumped actually, so my debouncing switch wasn't working so well. So that is of course 8 and 4, which is 12, 13, 14, 15, and back to 0. So that's all working perfectly. Just as a quick bit of testing, might be worth just looking at that when it's low. And if you'll notice that when the LED is on, that is not recognizing that as a high because of the voltage drop. but it seems to be enough for our 451 to recognise it as a high. This is sometimes the conflict between analog and digital circuits. But this is the end of this tutorial.